Welcome. In this video, we'll be discussing a rapid hand analysis technique in order to do analysis for multi-stage amplifiers. Multi-stage amplifiers, we're referring to amplifiers that have multiple transistors. Let's get started. So the purpose of this circuit analysis in general is to gain insight into the operation of a circuit that you're trying to design. If we're just trying to get the answer, if we just want to find what the gain of a circuit was, we can always run simulation. But if the circuit is not giving us the gain that we'd like, we need to know how to vary the circuit in order to change the gain of that. So during the design phase, we have a number of specifications that we'd like our circuit to meet. That may be the gain of the circuit, the frequency response, distortion of the circuit, so linearity, the noise, thermal noise or low frequency noise, power supply rejections, another specification, and so on. And we do hand analysis so we can determine what changes we can make that can improve our circuit to make it the gain what we'd like it to be, the frequency response faster, and so forth. If we're just trying to gain insight into our circuit, we don't need to get the exact value. We can actually allow errors in our estimate of what the gain might be or what the frequency response might be. So we might allow up to 15% accuracy of our when we're doing our rough analysis or our hand analysis. Now, this rough analysis is due to two issues. One is we're going to make an approximation. We'll see just in a second. The second is our models, our transistor models that we're using for hand analysis are not that precise. They're rough approximations of the actual transistor models that are used in simulations. So if you look in SPICE, the SPICE models are much more complex and would not be suitable for hand analysis. And so the hand analysis models are already rough approximations of what the simulator is going to give us. Since that's the case, another common approximation we can make then is to assume that GM-R0 is much greater than 1. In many cases, in the exact values for calculating gain, there'd be a term of 1 plus GM-R0. If we assume that GM-R0 is much greater than 1, we'll just approximate that as GM-R0. So if GM-R0 is 20 or above, the error that will be introduced will be 5%. In other words, if GM-R0 is 20, 1 plus 20 would be 21. So the exact value would be 21, but we approximate that as 20, which means we have a 5% error in our analysis that we're doing. And if we have a number of places where that occurs, they might add up and we might get 10% error eventually. Recall that having GM-R0 much greater than 1 is equivalent to saying that R0 is much greater than RS. And if you recall, RS is equal to 1 over GM. So to do this rapid hand analysis approach, we're going to rely on two techniques. One is to look at find the gain quickly by modeling our circuit as a current source equivalent, and then finding the output short circuit current, find the output impedance, multiply those two together, and we get the output gain. This is not an approximation, this is exact. The second is we would like to not draw the small signal model for all of our circuits. So we'd like to do our analysis directly on the circuit itself. To do this, we'll actually introduce simplified models for the transistor in common gate amplification, common drain amplification, and common source amplification. And these models will allow us to do our analysis directly on the circuit. The models have a little bit of complication to them, so generally we don't remember memorize all the equations here. We just have a table lookup to look at the different cases. So let's start at the first approach, which is to look for just how to find the gain for a circuit. So here we're looking at a method for finding the gain, V out over VI, for a circuit. In this case, we'll assume our circuit looks something like this, which has dependent sources, resistors, capacitors, etc. inside this circuit. In order to find the gain, the output voltage here related to the input voltage, we will first short circuit the output, as shown here, and find the output short circuit current here. That short circuit current will be a function of the input voltage. Next, we find the output impedance, shown over here, looking back into the output, and when we do this, we ground our input, so we zero the input because it's an independent source. Finally, to find the actual output voltage for this, we multiply the two together. We multiply our output short circuit current by our output impedance, and that will give us our output voltage, which will now be a function of VI, since the short circuit current is a function of VI. And that way we can find the output voltage relative to the input voltage. So let's look at an example here. So this is a simple resistor example, and we'd like to find the output voltage relative to the input voltage here. So if we use our technique, we'll find the output short circuit current, so we ground the output. If you go through the analysis for this, you'll quickly see that the output short circuit current is 2 over 5 times VI. If you then find the output impedance of this circuit, so we ground the input here, and we find the output impedance looking back into the output, we'll see that R out in this case is just 5 over 8 ohms. If we then multiply these two together, so if we have the V out is equal to ISC times R out, ISC was equal to 2 over 5 times VI, R out was 5 over 8. If we multiply those two together, the 5's cancel, and we have 2 over 8 times VI, so we have the result as we expect, in this case, that the output voltage is equal to 1/4 times VI. Now in this case here, we never worried about the intermediate node V1, so we went directly to the output. You can do that, but again, once we're doing an analysis, generally we'd like insight and we'd like to know the gains through the different values, through the different nodes. So we'd actually often like to find the gain from VI to V1, and then the gain from V1 to V out, and then the overall gain, V out would just be the multiplication of those two. So in other words, we'll find V1 over VI. We'll also find V out over V1. If we multiply those two together, that will be V out over VI. And the benefit of this is twofold. Number one, we find out the intermediate gains of our stage. And second, we'll see it's even easier to calculate this, generally speaking, than going directly to the output. So let's look at this approach here. So here's the example where we're now going to be finding V1 over VI, and then we'll be finding V out over V1, and we can multiply those two together to get V out over VI. So let's start off by the first part and finding V1 over V sub I. So we do this as we would normally do it. We see that V1 is in this location right here. So we find the short circuit current at this node, and we find the output impedance at this node. So for the short circuit current, again, we short circuit at this node here. We find that the short circuit current is just going to be VI divided by 1 ohm. Why is that the case? Well, we see once this has been shorted, any current that goes through here, I, is now going to go through here, I. And this will all remain 0, since this is 0 volts, and these are all 0 volts. So we can ignore all those components here. And we see that this current I is just equal to VI divided by 1 ohm. So we have our result, in this case, that the short circuit current is just equal to VI. Second, we want to find the output impedance looking into this node here. If we look at this result, or this case, we said this impedance looking into here is 2 ohms. This impedance looking into here is 2 ohms. 2 ohms in parallel with 2 ohms is 1 ohm. And that 1 ohm is in parallel with 1 ohm. So the whole thing just reduces down to 1/2 an ohm. So we multiply these two together, the short circuit current times the output impedance. We see that we have the gain from the input to V1 is 1/2. So V1 over VI is just equal to 1/2. Next, we need to find the gain from V1 to V out. Recall we've already found the gain at V1. So when we're dealing with the next stage, we actually will then take V1 and use an ideal voltage source and replace or attach it to this node, because we know exactly what that voltage is now. So we change our circuit from above to this circuit here. And this is the circuit we'll be finding the short circuit current as well as the output impedance. When we find the short circuit current, in this case, because V1 is an ideal voltage source, we always end up with V1 here, and the current that goes into this does not matter at all. So we can ignore this. The short circuit current then is again attached at this node, so we can ignore whatever happens here. In fact, there'll be 0 current going into that. So we just have that the output short circuit current is going to equal V1. Again, it's V1 divided by 1 ohm, where this is the 1 ohm resistor. So we have our short circuit current given by this equation here. Given by this equation here. Now we need to find the output impedance. For the output impedance, we recall we've attached V1 at this node due to this one here, but for output impedance, we set V1 equal to 0. The independent sources are always set equal to 0. So now we're just finding the impedance looking back into this with this node equal to 0. Doing that, we'll find that the output impedance is just going to be 1 ohm in parallel with 1 ohm, which turns out to be just 1/2 an ohm. So if we multiply these two together to get the output, V out is equal to the short circuit current times the output impedance, we get it's a gain of 1/2. So the key point to remember here is that once V1 has been determined, V1 is now assumed to be an ideal voltage source when we're finding V out. It's an important point to note. So finally, we now know that the gain from here to here is 1/2. The gain from here to here is also 1/2. So we have that V out is 1/2 times V1, but V1 is 1/2 times VI, so the overall gain is 1/4 times VI. Now we're going to combine the above technique that we just looked at with 3 types of single transistor amplifiers and models for these 3 types. So we're going to be looking at common source amp, common drain amp, and the common gate amplifier. We'll be first looking at exact models, and then we'll take a look at the exact same models, but we'll assume that GM-R0 is much greater than 1, and that will simplify the models for us. Our model derivations are at the end of these notes. The purpose for doing this is so that we no longer will need to draw the small signal model, even if we have complicated circuits. So the purpose of doing this is so we can do our hand analysis directly on the circuit that we're looking at. So these are going to be our small signal model replacements. And though they seem a little bit complicated, as I mentioned, these are not generally memorized. They can just be looked up in a table somewhere. So the first one to look at is a common source amplifier. A common source amplifier, we want to deal with the case where we actually have a source resistance R sub S. So we'll allow that to be a case. So what we want to be able to look at is change this into a model. So for this common source amplifier, by the way, the reason it's called a common source amplifier is our input goes into the gate, the output is taken at the drain, and the source is the common node for this. So the model that we're going to be using is shown over here on the right side. So it's a current source equivalent model where it has an output short circuit current and an output impedance Rx. So we know these 2 values that relate to the model or the common source amplifier on the left. So as I mentioned, the derivations of these models will be at the end of the notes. So the first thing is a short circuit current is given by this equation here. Minus GM R0 divided by R0 plus 1 plus GM R0 times capital R sub S and all times VI. We'll see a simplification of this when GM R0 is much greater than 1. And the output impedance for this, R sub X, is given by this equation, which is R0 plus 1 plus GM R0 times capital R sub S. And as I mentioned, this is all exact. There's no approximations made here at all. So whenever we see this type of transistor being used in a circuit, we can think of it as knowing what the short circuit current will be for this and what the output impedance will be. Now, the next model we want to look at is the common drain amplifier. So this is a common drain amp. The reason it's called the common drain is we're applying our input at the gate, taking our output at the source. In this case, the common node is the drain. So for this configuration, this common drain amplifier, we'll actually use a voltage source equivalence. So in this case here, rather than using a current source equivalent, we're using a voltage controlled voltage source here. And so for this case, we have the open circuit voltage, VOC, and that's given by this equation here. And we have the output impedance, R sub x, and that's given by this equation here. So R sub x is the impedance looking into the source of this transistor when we have a drain resistor. Now, if we don't have a drain resistor, of course, we just set this equal to 0. So the equations are shown here and here. And again, these will simplify once we assume that GMR naught is much greater than 1. So finally, we have the last amplifier. That's the common gate amplifier. The reason it's called a common gate is our input is applied at the source, our output is taken at the drain, and the gate is common. So in this case, we've grounded the we've grounded the gate, but we could add a resistor into that node and it would make no difference to the results here since there's no current going into the gate. So in this case, we'll use a current source model. So we have a current controlled, a voltage controlled current source, ISC. So it's a current source, dependent current source, but it's controlled by the input voltage V sub I. And we now have the output resistance R sub x, but we also have an input resistance Rn. So we have to worry about what the impedance is looking into this. So now we have 3 terms for this. And so the 3 terms that we have now are the short circuit output current, R sub x, which is the output resistance, and R sub in. So R sub in is down here. The output resistance is looking into this output node at this point. And the short circuit current, of course, is over here. Note that in this case, the output resistance, R sub x, is including the drain resistor, R sub d. It's shown here. Now, as I mentioned, we can find the exact same models, but when GMR naught is assumed to be much greater than 1, the models become somewhat simplified. So in the common source amplifier that we have here, we have exactly the same model, but the equation has been simplified somewhat. So now it's just minus 1 divided by 1 over GM plus R sub S. And the output resistance R sub x is now 1 plus GM RS times R naught. So you can see it's somewhat simplified than it was before. Still probably need a table to look it up, but it's a simpler model to use. For the common drain amplifier, here, this becomes quite a bit simplified once we assume that GMR naught is much greater than 1. So here we see that the output open circuit output voltage is just VI. And that comes about because if we go back to the equation here, we have that the output open circuit output voltage was GMR naught divided by GMR naught plus 1. If we assume that GMR naught is much greater than 1, this just simplifies to 1. In addition, we have the output resistance when GMR naught is much greater than 1, or assumed to be much greater than 1, is given by 1 over GM plus R sub D divided by GMR naught. So recall that's the impedance looking into the source of a common drain amplifier. And finally, we have the common gate amplifier. Again, we're assuming that GMR naught is much greater than 1. And so we have the output short circuit current is just GM times VI, which is quite a simplification. We have the output resistance is just RD in parallel with R naught. And we also have the input resistance is just 1 over GM plus RD divided by GM R naught. So now we want to use our rapid hand analysis technique to do a couple of examples. In both examples, we'll be assuming that GM R naught is much greater than 1 to simplify our life when doing hand analysis. So in this example, we're going to assume that all the transistors have GM is equal to 1 milliamp per volt. And we'll assume that R naught is equal to 40 kiloohms, which means if we multiply GM times R naught, we end up with 40, which means we'll only have about a 2.5% error each time we're making the approximation that 1 plus GM R naught is equal to 1. In other words, approximating 41 by 40. And we're going to want to be finding the gain V out over VI as well as the gain V2 over VI. We'll be looking at this circuit here, which is our cascode gain amplifier that we looked at before. So we're going to need some output impedances because we're going to be finding the gain at V out as well as the gain at V2. So what we know is we're going to need the output impedances at each of these nodes, and we're going to need the short circuit currents at each of these nodes relative to VI. So let's start off by looking at V out. So we first need to find the impedance looking up into the drain of M3. So we'll call that ROP. So we recognize first that the impedance looking up into M4 is just RO4, because this is just a single transistor with the gate tied to ground, because we're looking at small signal, so all our bias voltages will be tied to ground. So we know that the output impedance looking up into M4, the drain to M4 is just RO4. So when we see this transistor M3, we have to determine which type of transistor that is. Well, we're looking at the output impedance into the drain with the gate connected to ground. So if we go back to our models here, we're looking at this type of situation here. So we're looking at R sub x. So we're given by this equation, R sub x would be 1 plus GM of the transistor times the impedance R sub s, which in the case that we're looking at will be RO4, times R naught, where R naught is the R naught of the transistor itself. So we can just write down this value here, that the gain looking into the drain of M3 is 1 plus GM3 times RO4. We're using RO4 here because that's equivalent to the RS that we saw in the model that we're looking at, the common drain model. And so then, and we multiply this by the output impedance of RO3. So we end up with by inspection, the impedance looking up into the drain of M3 is given by this equation. And again, if we're assuming GM R0 is much greater than 1, and we can then recognize that this is a GM R0, it just happens to be the GM3 times RO4, but we're still, that's still going to be equal to 40, so we can make this approximation that GM R3 is much greater than 1. So this whole term here reduces to just GM R0, and that's multiplied by another R0, so the whole thing just becomes GM R0 squared, in which case GM R0 is equal to 40 times another 40, because R0, sorry, not times another, 40 times another 40 kiloohms, so it's 40 kiloohms times 40 kiloohms times 1 milliamp, and the whole thing works out to be 1.6 megohms. So by inspection, or by rapid analysis, we can see that the impedance RO4 is equal to 1.6 megohms. Looking down into the drain of M2, we can go through the exact same approach, and we'll quickly see that that value is also 1.6 megohms. So now we know that the output impedance, looking at node V out, is ROP in parallel with RON. We'll use that later on. Next, we need to look at the output impedance RO2, looking into node V2, because we're going to be finding the gain from VI to V2. So in this case here, we have that RO2 will be equal to the impedance looking down, which is going to be RO1, in parallel with the impedance looking up into the source of M2. And this is where we'll use one of the equations again that we have above. So in this case here, looking for this impedance looking up into the source of M2, we recognize that that's equivalent to a common gate amplifier where the drain resistance is equal to ROP. So if we go back up to our equations, we see that we're looking at this situation here, and RD in this case is ROP. So we make use of this equation, and we find that the impedance looking into this node here is just given by 1 over GM2 plus ROP, because that's equivalent to having the RD in the above equation, divided by GM R naught of M2. So we already know that ROP is given by GM R naught squared. So this is equal to GM R naught squared. But it's divided by, here, GM R naught. So the whole thing just becomes R naught. So this changes into just R naught. We know that R naught is much greater than 1 over GM2, so we can approximate this as just R naught. And so we have R naught in parallel with RO1, so the whole thing just becomes RO divided by 2. So again, without ever drawing the small signal model, we see that RO2 is just given by RO2, RO divided by 2. So now we found the output impedances at the different nodes. We now need to find the short circuit current. For V2, the short circuit current is straightforward. So for V2 here, ISC, when I short V2, everything above it no longer matters. So it's just relative to VI, so it's just going to be minus GM1 times VI, because we just have a single transistor here. So the short circuit current is minus GM1 times VI. So we have that V2, the output node V2, is minus GM1 times VI times the impedance that we just found, which was RO2. If we multiply those three together, we end up with this result here. And finally, we just plug in the numbers, 1 milliamp per volt for GM and R naught of 40 kiloohms, end up with the V2 is just equal to minus 20 times VI, or in other words, the gain from VI to V2 is just minus 20 volts per volt. Now when we go to find V out over VI, we have two methods we can use here. We can either find it directly by just finding the short circuit output current at V out and then multiply by the impedance of that node, or we've already found the gain from VI to V2, and so now we can find the gain from V2 to V out. So we can either find it directly at find the output short circuit current due to VI, or we can find the output short circuit current at V out, assuming that V2 is now a ideal voltage source. So let's look at those two cases. So we're going to look at the direct case first, where we find the output short circuit current due to VI directly. So first, we're going to be short circuiting this node here and finding I sub SC. What we need to find then is the current, the short circuit current. We already know that the current through here is minus GM1 times VI, but how much of this current gets to the output ISC? So just looking at M2 by itself. So for M2, well, we'll draw the small signal model, but in general we wouldn't have to do this. We basically have a connection here, and we're trying to find this current ISC. Well, because RO2 is much greater than RS2, in this case, almost all of ISC1 will go through IS2, and so the short circuit current will just equal IS1. Sorry, it will equal IS1. So, as I mentioned, I think previously, is that when we're finding the short circuit currents, we can generally make our output impedance all go to infinity. So currents just go directly through transistors in this case. So using this knowledge here, that most of IS1 goes directly through RS2, and because GM R0 is much greater than 1, we then have that the output voltage, the short circuit current at the output is minus GM1 times VI. The output impedance at Vout is GM R0 squared for ROP and GM R0 squared for RON. So it's divided by 2 because the two are in parallel. We multiply all this together. We'll end up with an overall gain of minus 800 volts per volt. Next, we'll look at the case where we find the output voltage, making use of the fact that we already know the voltage V2. So we're going to look at this case using V2 over VI when we find V out. So in this case here now, we've replaced the node V2 with an ideal voltage source. We want to find the gain from V2 to V out. So we start off doing what we normally do, and we find the output impedance at the node V out. And this is going to be ROP as we had before, but looking down in this direction, it will just be RO2 because we simply have a single transistor M2 connected to an ideal voltage source, and we set that ideal voltage source equal to 0 when we're finding output impedance. So it's just going to be RO2. Now if we look at the short circuit current, the short circuit current at this node, when we set that equal to ground, due to V2, this is a common gate amplifier. So if we look at our common gate amplifier, we have that the short circuit current is just given by GM times VI. So going back, here we have that this short circuit current is going to be GM2 times V2. The impedance at the node is RO2 in parallel with ROP. Now RO2 is 40 kiloohms. ROP we saw before is 1.6 megohms because it's GM-R0 times R0. So RO2 is much less than ROP. If the two are in parallel, this is going to be, you can pretty much ignore ROP, and it's just going to be approximately equal to RO2. So we can approximate this as minus GM2 V2 here times RO2, which is just here. If we multiply this together, we end up with V out relative to V2 is just given by GM2 times RO2. Finally, if we want to get the actual gain, V out over VI, we have the V out over VI is given by V out over V2 times V2 over VI. We have V out over V2 given by GM R0. We found from before this was equal to minus GM R0 over 2. So the overall gain is minus 800 volts per volt, which is the same result that we had before. So now let's look at a second example. In this example, we'll be wanting to find the gain from the input, VI, to the output, V out, over here. So this is a multi-stage amplifier. So we've got 3 transistors and a passive attenuator inside this as well. In this case, we'll be assuming that all of our transistors have GM is equal to 1 milliamp per volt, and the output resistance of all the transistors are 40 kiloohms. So GM R0 is 40 as before. In addition, we'll assume that each of the current sources have an output resistance of 40 kiloohms, the same as each of the output impedances of the transistors. We want to find V out over VI. To do this, we'll find the intermediate gains. So the gains from VI to V1, and the gain from V1 to V2, and the gain from V2 to V3, and finally the gain from V3 to V out. And then we multiply all those gains together, and we end up with the overall gain for this circuit. So let's start off by finding the gain from VI to V1. So we've redrawn this part of the circuit over here. Because V1 is going into the gate, there's no load at this node, no extra load that we have to add on. So we simply have this circuit here. It's not difficult to see, we've seen this case before. We can just find the output short circuit current here. That will be equal to minus G1 times VI. And then we can find the output impedance at this node here, looking back into this. And this will be R01 in parallel with RO1. This will be given by this value here. And so we multiply those two together and we get the overall gain as shown here. And that works out to be minus 20 volts per volt. Next, we want to get the gain from V1 to V2. So we will redraw that circuit as this one shown over here. Here we've added the load, because there is a load that we have to account for, RL2. So if we go back to our circuit, RL2 is the load looking into this part here. So we can see that RL2 is going to be R1 in series with R2 in parallel with this impedance RY over here. So we have that RL2, as I mentioned, is equal to R1 in series with R2 in parallel with RY. For RY, we can see that we're looking into the source of a transistor. So this is a common gate amplifier, looking to the source of M3. So it's going to be equal to, we've seen this before, it's equal to 1 over GM3 plus the drain resistance. In this case, the drain resistance is the output impedance of that current source, RO3, and divided by GM3, RO3. So that is using our table lookup, where this is the RD of the transistor for a common for a common gate amplifier. So if we work that out, our Y turns out to be 2 kiloohms, and then if we plug that into this equation, we see that our L2, the load for M2 that this transistor sees, is 19 kiloohms, or RL2. Now, once we've determined RL2, we recognize that this is a common drain amplifier. So it has a equivalent model that looks like this here. So an ideal voltage source of VOC, the an open circuit voltage, which is just equal to the input voltage VI, and that is driving a load or an output impedance RX, which is given by 1 over GM plus RD over GM R naught. So we just have to remember these two values, VOC and RX. So going back to our circuit. As I mentioned, we recognize that it's a common drain amplifier, and VOC is equal to V1, and the output impedance of this common drain amplifier is 1 over GM plus RD over GM R naught. In this case, RD is the impedance seen at this node here, and it's just connected to ground. It's connected to VDD, which is small signal ground, so RD is equal to 0. So we have that in this case, RD is equal to 0. So the output impedance, RO2, is just equal to 1 over GM, which is 1 kilo. So now we can see that for this common drain amplifier, or a source follower, it's just a resistor divider. So it's a resistor divider between the impedance of, it's a resistance divider between the impedance, the total impedance seen at the load here, divided by that total load, plus impedance of our source follower. So in other words, in this particular case, the total load we see is RL2 in parallel with ROI2 and RO2. So in other words, it's the parallel impedance of this impedance in parallel with this impedance looking down and this impedance looking up. So RO2 in parallel with ROI2 in parallel with RL2. So that's the load that we're driving. So it's that impedance divided by the same impedance plus the output load that our voltage source equivalent has. If we plug this all into these equations, we see that the gain from V1 to V2 is just given by 0.907 volts per volt. Now that we have the gain from V1 to V2, we go back to our circuit. We'd like to get the gain now from V2 to V3. This is a passive gain, there's no transistors in here, but we still need to account for all the resistive loads. So we need to account for the load resistance, RY, as well. So if we go to draw this by itself, you see that we have this circuit shown here, where RY accounts for the impedance looking into the source of M3. So we can see that this is just a straightforward resistor divider. So the gain is going to be R2 in parallel with RY, and divided by R2 in parallel with RY plus R1. We found from before that RY was equal to 2 kilo ohms. So we plug this all in, we end up with the gain from V2 to V3 is 0.0526 volts per volt. Our final stage is to find the gain from V3 to Vout, which is a common gate amplifier. So you recall we were going to replace V3 now with an ideal voltage source to get the gain from V3 to Vout. So we just redraw that. We have this circuit here, where V3 is an ideal voltage source. So if we find this gain, we see that the short circuit output current is going to be just going to be GM3 times V3, and the output impedance is going to be RL3, the impedance looking up into this current source, in parallel with RL3, which is the impedance looking down to into this transistor, because we're assuming V3 is an ideal voltage source. So we put this all together and we end up with the gain from V3 to Vout is 20 volts per volt. We then want to find the overall gain, Vout with respect to Vi. We can multiply that by V1 relative to Vi, multiplied by V2 relative to V1, V3 over V2, and Vout over V3. What we have is we'll be able to cancel out, sorry, did that wrong. We'll be able to cancel out the V1s, the V2s, the V3s, and we end up with the gain Vout over Vi, and that's equal to minus 19.08 volts per volt. So that's the end of this example and the end of this video. In the rest of these notes, it discusses the derivation of these different models to get the exact formula. You can go through those at your own pace. Thanks for watching.